So we have few questions for you. So I'll like one by one take them. I hope my screen is visible.
Yeah, it's visible.
So first, some questions for Mahesh. So first question is, what are key skill sets in hardware design that a new entrant should learn to become big in hardware design?
Yeah, so I think I briefly touched about it in my talk. So the fundamentals of electronics, right? So if you are good at the fundamental components of electronics, electronic components, uh, so that should be able to get you to start with, and then as you grow, right, and your problem solving ability, and it's about how quickly you can learn, uh, and becoming big, right? So uh, to that aspect, I would say, have a good understanding on the field theory, right? Because that's where the things get complicated, and uh, when let's say you have a high speed like 10 Gbps going in a line, and how do you actually design that, right? So as the frequencies and the data rates increase, uh, right, so the more complex it is getting, but having a good understanding of your basics in your textbooks really going to help you.
Next question. Okay, so I think you briefly have also answered this. What are the key skills that are expected from a student pursuing embedded hardware design? Anything
Yeah,
you
so
want to add?
yeah, just want to add, so basically digital logic, solving problem. I think if you had a chance to interface, right? I mean, see, these days you get a Arduino board which is tagged, and it works right out of the box. But if you get a chance, try to interface your microcontroller with different peripherals. Let's say you take a touch sensor or some LCD or LED display, right? And try to interface it on your own, right? That's where you get to see what exactly is needed to connect the things together in a hardware. So that will give you a good understanding.
Okay. Next questions for Nitish. What are the basic important areas that a student should focus while pursuing embedded software? How to proceed into this domain, especially for a student from non-programming background? Though you have answered it, but if you want to add anything, you know.
Yeah, so for a person from non-programming background, yeah, it's as we are talking from the embedded software perspective, which means that we need to understand how programming works. And as I mentioned, you may not require to have a hardware right away, but you need to come up with the logic. So you can, in your spare time, you can think about some small application, try to code it, and then what the other area is like looking for the worst case scenario. So when we call embedded program engineers, they always think about what could lead this to an error. So you try to test it, you try to break it and see if you can make it efficient, because when it comes to embedded programming, the memory, the resources are very constrained. And say we might have written a program in a certain way, but it may not fit into your controller, so you have to rethink of the logic. So the best way is like you try to practice and put it and see how efficient you can make it, and think of the corner cases. What if it happens? Say if I am asked to design a calculator, if what if there is a negative input that comes in? Well, is my code is enough to handle that, or how does it react? Because it's a device, right? So how it's going to act, how it's going to save or fail gracefully, all these things we need to think, and it comes by practice. So that's what I would say, like to program, to code and kind of keep an eye on practicing and just, yeah, go with hardware.
What are the languages that one should be good at when it comes to embedded software?
Okay, so when it comes to language, yeah, I would like to add, say, if you are able to learn at least one assembly level language. The reason I tell is these days it is not the main focus, unfortunately, because we have other high level languages that have come into picture. But I actually understood many things when I personally code with the assembly level language, because that directly deals with the hardware. You know how each and every bit is moved into the registers, and when you read it, what happens. So that will give you a solid understanding about a controller and its architecture. Again, it depends on the architecture. There are other various architectures on that as well. But apart from that, if you are focusing on C language, that should be good enough for you to get into this embedded software. So that is one. And if you can learn C++, a kind of object oriented, that would help you to think in terms of abstraction and all those object oriented concepts. So many of the libraries like Linux OS and all, it has many libraries that are in C++. So I would suggest both C and C++ as the languages.
So now questions for both of you. So what are the major challenges in embedded systems? So Mahesh, you may go first.
Yeah. So so embedded systems. The main challenge is you have a limited resources. Okay. So limited resources in terms of your processor, limited resources in terms of your battery, right? So how optimized is my design? Okay, that and in terms of memory also, like Nitish was pointing out. So when it especially comes to the hardware design, like how efficiently I can design this, which means how long, how what is the largest battery life I can give for this particular design, right? Because most of your embedded systems comes, I mean, let's say 80 to 90% are battery powered or remotely connected, right? And then the reliability of it. Let's say you are deploying some in the field, right? In a remote field and it's no humanly accessible. So let if it is not reliable, right? If the communication breaks, then no way that it's going to serve your purpose, right? So these are some embedded system level challenges that we need to keep in mind.
Nitish, you want to add something?
Yeah, so as I mentioned, so when it comes to embedded, so I would talk about the embedded more on the embedded software side. So coming up with a scalable and a secure software is a challenge that we are also facing these days, because as the demand for this scalable software with low footprint that is the industry expects, right? Uh, to come up with the optimized way of softwares with the limited hardware resources that we get is a kind of challenge that we are always faced with. So we may not always get the freedom to have all the resources in it. So we might will have to try to kind of encompass the logic within a certain limit or certain time, that I would say. That's where the challenge as embedded software engineers that we are facing today. Excuse me.
So second question is, how difficult is it for one to relate the topics from book to practical implementation?
Yeah, so I think the question assumes that the practical implementation is something different from the book, but in reality, we engineers even as we grow in experience, right? So we keep coming back to the books. Okay, so there is nothing magic happens between the books and what is practical. So what is actually happening in the practical is from the books. So I suggest that keep both in a synchronous. I mean, both are the same. There is no gap, and it's very easy. As I was also trying to point out in my talk, I was trying to relate right with your with the circuit that we read in the book. So that's where it starts, and the basic starts from your book, and it's very practical to relate to.
Yeah, so as Mahesh mentioned, right? So what I see as a missing thing is that bridge. So when we read about something, say a concept like FFT, we actually never realize where it is actually used. But as I've in my over the period of my career, I got onto kind of understanding how these are being actually used. Say if you have got an opportunity to work in an audio domain where these concepts are will play a major role, you will have to implement the filters, FIR filters, to have these audio applications coming. And vector algebra is one area in mathematics where it is being extensively used in video, especially when I worked in camera domain. So everything was like vector, because the camera, the image, finally what we call is based on pixels. So there, that is where the practical applications of what we have learned has is coming to picture. But the thing is, when we are at the college level, we might not be able to relate these things. So that's where I feel if there is a bridge that connects, okay, this is how it's being used, then I feel it would actually create more interest to understand those concepts.
So there are some questions in the chat. I'll take those up after the questions we have listed. And you can also post more questions and also can wait and just ask them yourselves. So it's like a question for Mahesh. What job opportunities can a student who has a master's in photonics and nanoelectronics expect in this field of hardware design?
I think this has come up early. So let me just say it again. So yeah, so photonics and nanoelectronics. So especially in terms of your networking and high-speed network like 100 Gbps and 400 Gbps networks. So this photonics is where mm, like the data gets transferred, and even in the recent advancements, even the photonics at the board level, right, at the hardware level, uh, because as the data rates increase, the challenge to transfer on an electric medium is going to reach its limit, right? So that's where the photonics is going to be the upcoming way we achieve a high speed data rates. Uh, yeah, and that's where it actually helps.
So we have also discussed this, that what are the job opportunities in embedded hardware, but if anything more you want to say?
No, we have covered that.
Okay, thank you. Next one, please. The same. What are the job opportunities in embedded software? If you have anything to add.
Yeah, so as I mentioned, right, there are various branches in embedded software. So it depends where you want to start ahead with, like start with either it could be a bare metal, you can go there from a driver programmer, then kernel if you are interested in Linux, or if you are interested in this network IoT, you have there also again these days we have a very good opportunity in the area of security, like where the hardware also is kind of the software that we write also needs a kind of secure thing. So where you will get to work on the cyber security things, we call it embedded IoT hacking. So you have many opportunities in embedded software as well, but it all starts where you want to go and which direction you want to take.
So Mahesh, what can you talk on the masters in embedded hardware?
Yeah, it's I mean, not a compulsory thing, but it's good to do. I mean, most of my colleagues and including me have started our careers without MS because no, to start like an entry level MS is not usually asked about in the job profiles of most of job profiles I go through. But having MS and having advanced degree is good. And if someone is looking to be expert in a embedded domain, right, in a specific, no, especially these days, IoTs, right, Internet of Things. Yeah, having embedded hardware, MS is good, and even including myself, have studied MS, MTech in embedded.
Which part, analog or digital design, is more complex and tough?
Yeah, that depends on the background. For a typical EC engineer, right? I mean, if you're good at digital, so the digital circuits are comparatively easy to solve your logic, right? Whereas analog circuits, as I said in the talk, right, you're transistoring in the linear region, and that gets into all the problems. Okay, how do you accurately fine tune your currents, right, in the circuit, and any noise, right, even in the millivolt scale, is going to affect you adversely. So I would say analog circuits are a little bit of complicated and tough, and there are very less experts in the industry currently, right, who can actually do a good analog circuits, especially the debugging part of it is very complicated. And also just keep it in mind, every signal is an energy, right? So let's say if you're sending, and every energy it is tend to radiate and emit. Okay. Let's say, I think if you have ever noticed, if you keep your mobile close to your TV and if you're getting a call, there are chances that your TV getting distracted because of your signal. So those kind of issues are predominant, and there are a lot of other issues. So that once we get into the RF, yeah, that part of is very. I wouldn't say it is very tough, but it is tough.
So next question for you, Nitish. How do you see the software flow from writing it on screen to practically seeing it stored and executed on computer?
Yeah, so it's a very good question. So when it starts with writing it on a screen, right? So say you write some logic, so you have a device and you have something to build on, and the first thing that I would think go is how my component wants to react. So as I mentioned, I use sort of simulator to first understand how things work in my software. So I try to come up with the algorithm, we call it algorithm, and or the pseudo code, whatever it is, and then try to run it in my simulator and see how it works, how it behaves. And then once, if I'm confident enough that what I have written works well in the simulator, the next thing is I would really test it on the hardware and see how it reacts. There the conditions could be different, and when I try to program my device and see, and when it up and I mean runs, that's where the flow is getting into. So there could be issues that you are facing in the hardware, which the software might be working good, but you are facing some kind of glitch in the hardware, when especially when there are components that are connected, multiple components that are connected. So this is a kind of flow. Typically, as we embedded engineers, we try to code and then directly program into a device. So I would suggest, if there is a simulator that you use, it would actually help in protecting your device as well. There could be causes of getting the device damaged also if we have not properly gone through the data sheet, and if we there are chances to corrupt the memory. So all those things can happen. So it is good for us to understand the hardware, and keeping in that mind, try to write the code.
Yep. So let's now take the questions from the audience. I have few questions in the chat box. So first is from Supreet M. What is the difference between a kernel and operating system?
Okay. So when we say operating system, it involved, it has a lot more responsibilities than a kernel. Kernel is just a part of the OS, so it may assume certain responsibilities but not the complete thing. So when we call an OS, its responsibility could be right from booting the device to getting you to the application layer. But a kernel is really kind of critical inside this OS, where it could assume certain responsibilities like managing the resources, the memory, or handling the device, the pins or other kind of peripherals that are inside the OS. So kernel is kind of one part inside the OS, but the OS encompasses everything inside, and it takes the responsibility of getting the application from right from the boot stage to the application layer.
Mahesh, you wanna add to this?
No.
Okay. So next question is from Ayushman. I want to pursue embedded systems, a system using ARM architecture, mobile processors. Would learning FPGAs help me in this domain?
Yeah. Okay, so learning FPGA, how does the learning FPGA helps in this domain? That's the right question.
Yes.
Okay, so yeah, as I touched upon, your FPGA is right. It is basically a memory. Okay, if I say, and it depends on what logic you put into that. So pursuing a career in ARM design and ARM core design, if you're doing micro architecture design, definitely you can learn FPGA. So FPGA is a part of design cycle of any processor, right? So you first design any processor in your HDL, hardware description languages, Verilog or VHDL, and then you port it on your FPGA and see what your logic design, what you wanted is really working. Okay, so that's called FPGA porting. So that is a major step in any silicon development and design, right? So if you can learn FPGA, so there are a couple of ARM cores you will be able to instantiate, right, into your designs. Let's say if you take a Xilinx or Altera, there will be a soft IPs of your ARM cores, not your latest or greatest core architectures, but some commonly released in the market. So you can start with that, right? And then if you have a FPGA development board, what you can actually do is you put your synthesized netlist in the FPGA and try to load your software. You can actually boot your operating system on top of FPGA with ARM core, and then over a period you will understand more about FPGA as well as your ARM architecture, right? So that way, nothing is going to be a loss. It's good to learn FPGA, by the way. Yeah, irrespective of which architecture you finally end up working.
Okay, great. We have two more questions from Spreet. When you mean layers, do you mean they are a bunch of libraries which can be called and not worry about its execution?
Sir, can you repeat? Is it for me?
It's no one's name is mentioned, but I think you may take. When you mean layers, do you mean they are a bunch of libraries which can be called and not worry about its execution?
Yeah, I think it's for Nitish. It's
It's for
about the
Nitish,
software
yeah.
layers.
Yeah.
Okay, so maybe I think Supreet, if we can give me the context on layers, like uh, which on what context the layers is being like discussed about. It is about the Linux or any other software, because I'm not clear on.
Here's a follow-up question. Does that mean Linux kernel layer is the one that does the actual work on the hardware component?
Okay, so it's about a Linux kernel layer, is it right? Okay.
Yes, sir. It's about
Uh,
Linux.
Okay. So say when we say layers, right? So if I want to use an analogy, what maybe I can think of is, yeah, this network layer. I'm not sure if you have read about the network or the ISO layer we call, where it starts from a physical layer and flows through the application. It has some 6 to 7 layers. So even the Linux or any architecture, if we see, they divide into layers so that each layer can take its own responsibility. So especially when it comes to operating systems, there are several responsibilities that this particular operating system has to take. So they will generally divide those layers, like say kernel will assume certain responsibilities, especially on managing scheduling. We have all these tasks that needs to be scheduled or handle the resources to the upper layers that are being asked. So that is where the layers come into picture, and when at what layer we are working may change, and it depends on how we want to take it from there. So sorry, I didn't get the second part of the question. So this is about the layers that the first question that we I was trying to answer.
So if you mean the layers, that means which is that layer which does actual work where the signals are, it takes the values from the register, goes to the processor, does the computing and brings it back.
It is the final hardware layer. So anything that we need to process finally gets into the hardware. But how it gets into the hardware? Say if I want to talk about the Android, right? Android architecture, it is also following on the same Linux kernel. Say when you tap into a camera icon, when you tap that camera icon, what it does, the upper application layer passes its control down to the hardware abstraction layer. It calls a camera API that is provided by your kernel, then it passes to the hardware. So the hardware now understands, okay, now I got a call for a camera to be invoked, to be turned on, so somebody has to do it. So there is a hardware, camera hardware, that is interacting with the other SoC, right? So there is a communication that is happening. So the low driver layer is where these interactions with other peripherals are happening, and once we get the response, we get the handle back and it is getting received to the application.
Okay, thank you.
There's a question from Harini. Are there any particular software that can show particular low-level instructions being executed by an off-the-shelf commercial controller chip, not the waveform observable at GPIO?
Yeah, so most of the IDEs, it depends on the vendors, the chip manufacturing vendor. So any good manufacturing vendor would provide the typical ID where it would show the instruction execution cycles, the binary map that we call, all those things. There are certain softwares, like say, since I'm from microchip, so we have this MPLAB ID which provides you that the moment you code a program or device and then you put a hardware debugging breakpoint, you would definitely see the execution in terms of the values or that you have set in execution. And yeah, there are these tools that are available as far as I know. So I am not aware. Yeah, there are other compilers like Keel is a kind of ID that I remember for the Atmels one, and I think AVR also has certain ID which provides this execution level kind of view where we can step into each and every instructions.
Yeah, so most of the code, the IDEs provide that. Just you need to set a breakpoints and in your flow of execution, and then see, at what stage, what register has what data, right? So that's where actually it gets really interesting.
Yeah, so we get into debugging
These
mode.
accessible for like chips used on some customized boards too, wherein your the board vendor like specifies that you can use only a certain subset of IDs.
Yeah, so in that case, that's where so if it is a very custom board, and if we don't have an kind of ID that supports, the only way that I at least know or I've done is like read the binary. At the end you will get the binary dump of your code, right? So we there are certain binary viewers where You can get that binary out of your device or the microcontroller and see what is happening there. And we have actually done it, but it is not as easy as any other ID would provide.
Thank you.
Yeah.
Any more questions from the audience? If not, then let's conclude today's session by presenting a small virtual plaque to our speakers. So first it's for Mahesh. Thank you for taking your time and delivering this talk. I
Hey,
think
thank you, Ananta, yeah, all the hosts. So thanks for giving me this opportunity. Thanks a lot. Appreciate it.
yeah, thank you. It's a pleasure to host you. Next, to our second for our second speaker. Thanks, Nitish, for this talk. And both the talks were very engaging.
Yeah, thank you for inviting us. And yeah, it was a very interactive session. We hope it gave some useful insights to our hearers. Thank you for the opportunity given.